Okay, in this video I wanted to finish up the info about summation notation, and so we talked about summation notation in the last video. It's a way to add up a bunch of things, and of course this notation is used for convenience. Okay, if you have many things that you're going to add up and there's, all the terms are a certain form, like it's easier to kind of write it in more of a compact form. And so we looked at some examples there, and I talked about some special summation formulas. These are ones that you want to know just because they do come up quite a bit in these early sections here in Chapter 5. Now, if we look at an example, this is kind of a neat historical problem, actually. We sometimes call this problem an example of what's called the method of Gauss. And suppose that I were going to add up the first 100 counting numbers. Okay, here's what that would look like in terms of summation notation. I got the sum as I equal 1 to 100 of I. Okay, and so in the expanded form, we're looking at 1 plus 2 plus 3 plus 4 all the way up to 100. What is that? Well, so this is kind of a neat historical problem. Sometimes contributed to Gauss. Gauss was, of course, a famous mathematician. About 400 years ago he lived, and the story goes that he was a student in a class. He was a young boy at the time, and the teacher wanted to get some stuff done, and so she gave the class a problem, and it was to add up the first 100 counting numbers. Okay, and of course they didn't have calculators and all that back then, so she thought this would be, something that might take some time for them to think about. And really, in just a matter of seconds, Gauss came up with the answer, and he said it's 5,050. And so she turns to him and says, "Yeah, that's correct. How did you get that so quick?" And he saw a pattern in the calculation. Okay, many people would do the problem like this, where they do 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, and if we do it like that, we're going to spend some time on it, right? There's a quicker way to do this, though. Okay, if you take the first and last numbers and add them together and then work your way towards the center, check it out. 1 plus 100 is 101, 2 plus 99 is 101, 3 plus 98 is 101, 4 and 97, that's 101. You're always going to get 101, right? Now, as you work your way towards the center, the last two numbers that you'd be using would be 50 and 51, which when you add together would be 101. So because you're always going to get 101, there'd be a faster way to do this problem where you just simply take 50 times 101. There's going to be 50 times where you get 101, and if you multiply 50 and 101, you get 5,050. Okay, pretty cool. But he was actually using this formula in disguise. Okay, this summation formula. N is 100, right? And of course, 100 over 2 would be 50. You got 50 times that you're going to get 101, so you're multiplying to get the result. But it's kind of using this formula here in disguise a little bit. All right, let's take a look at just some typical problems that we're going to see coming up here in the book involving summation notation. All right, here's an example. Let's evaluate the sum as I equal 1 to n of I times 4i squared minus 3. Okay, well, I'll go ahead and distribute the I into these two terms to begin. And now I know that I can split a sum into two sums. As long as I'm adding or subtracting, that would be allowed. And I also know constants can come out of sums. Okay, so let me go ahead and do that next. I'm going to split this sum into two sums, and I'm going to bring the constants outside. 4 and the minus 3 are going to come out of the summation notation there. Now I'm going to use my special summation formulas so that I can lose the summation notation. The sum is I equal 1 to n of I cubed. That one is right here. N times n plus 1 all over 2, the quantity squared. And of course, make sure that you lose the summation notation. You've applied the formula to be able to do that. minus 3 times the sum as I equal 1 to n of I. Well, that's n times n plus 1 over 2. And again, make sure that you lose the summation notation. You've applied the formula to be able to do that. So at this point, we would just simplify as far as we can go. 2 squared is 4. The 4's would cancel there, right? And I can bring the power of 2 into these two expressions. And then if I get a common denominator here, multiply top and bottom by 2 on this part, and then get a single fraction, then let's see, in the numerator, n plus 1 would be in common to these two groups. Also, n is in common to these two groups. So let me go ahead and factor out an n times n plus 1 out of the whole thing from the numerator. The leftover in the numerator then on the first group would be 2 times n plus 1, and then minus all that would remain from the second group would be the 3 there. 2n times n plus 1 would be 2n squared plus 2n, and so I think what I have here would be as simplified as we can get it. Okay, now the nice thing about having this formula created is because now if I were to let n be any number, I can know the sum right away as long as the terms are of this form. Okay, so like if n is 5, I'm just making up a number here. If I want to add up the first 5 terms, then n is 5, and so I could say 5 times 6 times, okay, 5 squared is 25 times 2 is 50, plus 10 would be 60, minus 3 is 57, all over 2. I'm getting 855 then as the total. Now that would be way easier than expanding out 5 terms and then adding up those, simplifying and then adding up those 5 terms. And of course, if I were to do many calculations, involving a formula, that you would see here, like I'd want to have something in a simplified form where I could just plug in the n value. Okay, so like if I were to want to add up the first 10 terms, I could just, n is 10, I can know what that is very quickly. Okay. A lot of the problems that we'll be doing coming up are going to be working with summation notation, I mentioned that, but also there's going to be some more limit calculations here. So let's take a look at, here's another one. Find the limit as n approaches infinity of the sum is I equal 1 to n of 3 over n times the quantity I over n squared plus 1. Okay, this type of calculation that you see here is going to come up in chapter 5 when we compute areas. You'll see that in the next couple of videos actually. So, well, I'm going to take care of the limit as n approaches infinity at the very end of this. Really the problem should be handled kind of like the first one, where I want to look at what this summation would be like in terms of n, but without the summation sign. Okay, so let's go ahead and start simplifying this. I can split this sum into 2 sums, and I can also pull the constants in front. Now, I is the index. Okay, so anything involving I would have to stay inside the sum. Anything else can come in front of the sum. Okay, so n cubed is a constant, 3 over n cubed, that's a constant. That can be pulled in front of the summation notation. 3 over n is also a constant that can be pulled in front of the second sum. Okay, you don't have to bring a constant in front. That's, you could certainly leave it in. There's no problem with that. Okay, so I've split that, pulled the constants in front, and now I'm going to use my special summation formulas in order to lose the summation notation. In the first one, the sum is I equal 1 to n of I squared. That's formula 3 here. It's n times n plus 1 times 2n plus 1 all over 6. And then on the second sum, you're adding up 1 n times, well, that's where I would just take n times 1 is n. Okay, so I'm using the first formula there. And again, make sure that you lose the summation notation. I'll have students continue to write the summation sign. Don't do that. Okay, you've applied the formula to be able to lose the notation, which is good because now we're back on familiar ground. We don't have this sigma sign involved in the calculation. Okay. Now, and of course, make sure that your limit notation looks good, okay? Be sure that you're writing limit as n approaches infinity, okay? Now, let's see. So I want to be able to calculate this limit, okay? The n's would cancel there at the end, so I'll go ahead and do that. That'll leave me with 3. And then with this part, okay, n cubed, that's the same as n times n times n. And that 3 over 6 is the same as 1/2. Okay, so the n cubed, let me write each n underneath each one of these 3 expressions. N over n, those are gone. N plus 1 over n, you can split that into 2 fractions. That'd be the same as n over n plus 1 over n, or 1 plus 1 over n. On this part, 2n plus 1 over n, let me split that into 2 fractions. So it's going to be 2n over n plus 1 over n, or 2 plus 1 over n. Now the idea with simplifying is that I want to write my terms in the form 1 over n to a power so that I can calculate this limit here, and I can also use my limit laws. So at this point, I think we can go to the answer using our limit laws. The limit as n approaches infinity of a constant is always the constant, right? Limit as n approaches infinity of 1 over n, that'd be 0. Since the denominator is going to grow without a bound as the numerator just sits at 1. So I've got 1 plus 0 is 1, and then 2 plus 0 is 2. Limit of a constant is always the constant. The 2's cancel, and so we get 4. Okay. Now, the meaning of 4 we'll see in the next couple of videos here. Really, this is just kind of a computational exercise to just kind of show you the type of calculation that we'll be dealing with coming up here. All right. I have some homework that I'd like you to look at. In the notes, there's a handout that I had where it says sigma notation up at the top, and here's just 20 problems that I had selected. Some of these are in the book in Appendix E, and some of them are from another source that I have, but I'd like you to look at those problems for me. All the answers are on the next page there, okay, and so be sure that you get the practice working with sigma notation. We will need to use that, and it will be super important, as I mentioned earlier in the last video. When you get into Calc 2, you'll be using sigma notation a lot, okay? So be sure to look at those problems for me, and I would also add that if you have a chance, maybe read over or look at Appendix E, which is at the back of the book. That is just a kind of a section on sigma notation. A lot of it I've already kind of talked about. Okay, but it's if you want some more examples, some more to look at, I would encourage you to take a look at Appendix E there.